Hello and welcome back to this series of lectures on linear algebra. In this lecture I will present some key aspects of the theory behind geometric vectors. In the last class we looked at 2D vectors, which you see represented somewhat in the left graph, and this time we're going to go a little bit beyond that and we're going to have a look at 3D vectors, which have a very similar structure to 2D vectors, and you see represented on the right side. And then we're going to try and make some relationships, some connections between the two, and I'm going to talk about why they are both together called geometric vectors, although somehow I suspect you know already. And then this will be used later on as a sort of a trampoline, as a starting point for everything else is going to happen in this course. So let's start. 3D vectors. So what are 3D vectors? They're pretty much, as I said, like 2D vectors, two-dimensional vectors. Just add water? What are you talking about? No, well, we're going to add something, but it's not going to be water. Okay, we're going to add another entry. So what do we mean by a 3D vector? A 3D vector is simply an ordered triple of scalars that we can write as v1, v2, v3. Notation is the same or very similar to the one we used for 2D vectors, except we're now using three numbers. And remember that the order here matters. By the way, these numbers better get their own name, and we're going to call the three numbers that make up a vector, both 2D and 3D, their components. So the components of a vector, of a geometric vector, are simply the three numbers that we use to define it. We're going to use the same terminology for two-dimensional vectors from now on. Now, a 3D vector also has a geometric interpretation. Of course, that is why we're going to call these geometric vectors. And it has the same interpretation as a 2D vector, namely a directed segment in space. So if we're now looking at three-dimensional space, so we're going to have an X and a Y and a Z component. This is something I'm sure you're very familiar with from your physics and statics courses. We can draw a directed segment as an arrow. And so if we look at this vector v, you can imagine just looking at the projection of this vector onto the xy plane, which will then generate their x and y coordinates, as well as the projection onto the z axis. We're going to look a little bit more in depth at what these projections are later on, once we have more tools to analyze them in depth. For now, I'm just relying on your own intuitive understanding based on previous courses. So for the given vector v, whose components are v1, v2, and v3, v1 will represent the distance, if you want, from the tip to the y-axis, assuming that the tail is at the origin, and v2 is going to be the distance from the tip again to the x-axis, but both the v1 and v2 will be in the xy plane, and v3 of course is going to be the height, so the distance above the xy plane along the z-axis. Again, I'm not being too fussy here in terms of specific descriptions. I'm going to rely on your usual intuitive understanding of these things, because really later on we're going to go way beyond this geometric interpretation, and we'll leave the geometric interpretation behind. Keep in mind that as for 2D, the position can change. So that is just one representation of the vector, but I can draw another one somewhere else, starting at a different tail point and ending at a different tip point, as long as the difference between the tip and the tail in all the three coordinates is going to be given by the three components of the vector. Notice how I'm now starting to relate coordinates of the point and components of a vector. Be careful not to confuse the two. The components are for a point, and the coordinates are for a point, and the components are for a vector. Now, the tip and the tail points are defined as before, so I'm not going to dwell too much on those. But I'm going to spend some time on some different aspects of terminology having to do with 3D and 2D vectors. First of all, as I mentioned earlier, we're going to call them geometric vectors simply because of their interpretation as directed segments. We can actually see them, we can visualize them, we can interpret a lot of their properties in terms of geometric properties, some of which we're familiar with, some of which we're going to learn as we go. some of the geometric properties that these things, again, that these vectors have as directed segments can be stated algebraically, and in fact it is the algebraic perspective that we will focus on, that will be deepened and strengthened, and we're going to go very much into the depth of these algebraic properties. Again, we're going to use the geometric vision just to have our eyes and our mind's eyes help us in understanding what some of these things mean and what we can use them for and how to interpret them and so on. But we're going to go beyond that, mostly into the algebraic realm.